Okay. All right. Well, happy Wednesday. Today we will talk about Bootstrap. Week 9, and it's March. It's I don't know if I should be surprised. I shouldn't be, because every day is 24 hours. It's been this way my whole life. But yeah, sometimes the months catch me off guard. But anyway, here we are, week 9. We are talking about, on Monday, we did randomization tests, and today we will do Bootstrap. And these are all both kind of ways for us to do statistical inference. And they're computational ways. So all of the ideas for statistical inference are based on the idea of the sampling distribution. And the sampling distribution is, what is the distribution? What is the distribution of all possible values of a sample statistic for all possible random samples drawn from a population? So the idea being, when you do a hypothesis test, you have a null hypothesis, and the null hypothesis says, I'm going to assume that the population looks a certain way. We assume the population looks a certain way, and we say, if the population looks a certain way, this is what my sampling distribution will be like. I can get these kinds of samples. It's going to be unusual to get this kind of sample if I'm assuming this to be true about the population. So we need to know this sampling distribution. If I'm assuming the population has a mean of 20 and a standard deviation of 2, then my sampling distribution will have some kind of property, also with a mean of 20 and something else. And it would be shocking to us if I get a random sample where the mean is 30, or it would be shocking to us if I got a random sample and the mean is 10, something like that, okay? So that would be, that's the idea of a sampling distribution. It tells you what kind of sample values you can get. And so by studying the sampling distribution, we get a sense of how much this sample statistic can vary from one sample to another. And if you have an actual sample of data, you can compare the statistic in your observed sample with the sampling distribution that would exist under this null hypothesis. And we can say, well, how unusual is this sample compared to the sampling distribution? And we get something like a p-value, and that helps us make decisions. In Stats 10, or your intro stats class, AP stats, whatever it was, you had the central limit theorem. And the central limit theorem says, anytime you're dealing with the sample mean, it's going to follow the normal distribution as long as your sample is random and as long as your sample is large enough. And so we have X bar comes from a normal distribution where the mean is mu, same as your population mean. Standard deviation is sigma over the square root of n. Sampling distributions technically exist for any statistic, not just the sample mean. It's just that when you're dealing with other statistics, say like the standard deviation or the variance or something like that, they're not going to be governed by the central limit theorem. So we can't say that this thing is going to follow the normal distribution, right? Like if we're going to try to model the variance of a sample, that's not going to follow a normal distribution. If we try to model the some other value, it's not necessarily going to follow a normal distribution. So what do we do in these situations? Well, we might have to kind of go through our mental archives, or we might have to search things online and try to figure out what theoretic probability distribution we can use to solve our problem, okay? But an alternative is we can run a simulation to get our sampling distribution. We just have to make some assumptions about the population. And effectively, in all of statistics, you have to make assumptions. So here we're going to be making some assumptions, and maybe we're comfortable making assumptions. Maybe we'll be in situations where we're uncomfortable making some of these situations. So, but at some point, you've got to make assumptions, right? Because the whole idea of statistical inference is that we're going to look at our sample of data, and based on our sample, we're going to draw conclusions about the population. Okay? And so anytime you have to make a leap from one thing and generalize to something else, that's an assumption, right? We're assuming that my sample looks kind of like the population, or we're assuming that the population looks a certain way. So we might have to make assumptions about the population's shape. Maybe we say, I'm assuming the population is normal, or at least unimodal and symmetric, or I'm assuming the population is uniform, or I'm assuming the population has this other shape. We might have to make assumptions about the population's mean or standard deviation, that they have this certain properties. We might have to make assumptions about what kind of values are we going to see in the population, that maybe we're not going to see a value bigger than this number. And once you establish your assumptions about the population, we can run a simulation to figure out what our sampling distribution will look like. And we're going to do this just by kind of drawing a random sample from the population, and we're going to just repeat this over and over and over again. And every time we draw a random sample, we're going to record whatever sample statistic it is that we're looking for. So let's look. So let's do parametric bootstrap. Okay. So parametric bootstrap. So we're going to look at two types of bootstrap today. There's parametric bootstrap and non-parametric bootstrap. And when you hear the term bootstrap, just used without any kind of context, or I mean, at least in the context of statistics, but nothing else, it's probably non-parametric bootstrap. But I like to discuss parametric bootstrap because it's also very useful, right? So when parametric bootstrap, we're going to make parametric assumptions. We're making parametric assumptions about the population. The term bootstrap for the statistical method comes from the idea of pulling yourself up by your bootstraps, and that's kind of like, you know, getting the job done without any additional help. Which, you know, sometimes if somebody just says pull yourself up by your bootstraps, that's another way of saying I don't want to help you. But in this case, when we, as far as bootstrap goes for statistics, it's the idea of, can we do inference without gathering more data? Because collecting data, gathering data is often slow and expensive. So can we get the job done without having to gather more data? The origin of this phrase, pull yourself up by your bootstraps, is disputed. But one theory that I like, so I'd like to mention it here, is that there's a story of some folk hero walking along, got himself stuck in a swamp, and the way he got himself out was he grabbed his bootstraps, pulled himself out of the swamp. Okay, of course, a ridiculous thing, but it's funny enough. Okay, so anyway, with parametric, it's like every time I talk, it wants to. With parametric bootstrap, we're going to assume the population follows some specific parametric distribution. And so you can say, you know, I'm going to assume the population, you know, if let's say we're going to do some kind of inference about the heights of people. So maybe we'll say, you know, in the United States, the average height of adult women, making up numbers, we'll say is 5'4.5", okay? And their standard deviation is 3.1, okay? And I'm just making up those numbers. And you can do that, right? If you just say, hey, I'm gonna just assume that the average is this and the mean is this, that's fine, okay? Now, somebody might say, well, how do you even know that, right? How can you just pick those numbers? And I just, well, those numbers looked nice. Maybe a better answer would be, okay, you know what, let's gather some data, and then maybe in my sample that I've gathered, the average is 5'5.1", right? 5'5.1" is my mean. So now I'll use that as the mean of my population. And maybe in my sample, the standard deviation is 3.4. So I'll use that as my samples, as my population standard deviation. So you can take values from your observed sample and use that to specify the distribution, okay, your parametric distribution. You're still assuming the population is normal and it has certain values and certain statistics or certain parameters, but now at least some of those numbers are grounded in reality because they're based off of a sample that you've collected, okay? But anyway, now that you have an assumed population, what we're going to do is we're going to simulate our sampling distribution by just randomly sampling values from this population. Every single sample you select, you calculate your sample statistic, and from there, you create your sampling distribution. Okay, so the SAT exam, there's like the math and the verbal side. The verbal is technically called evidence-based reading and writing. I don't know, you guys took the SAT? A lot of you, I assume. It's optional now, or maybe it's not even required. I don't even know what's going to happen in the future for UC admissions. But they're it's optional, and they might phase it out entirely. We'll see what happens. But a lot of students have taken it, and it's designed to be normally distributed with a mean of 500, standard deviation of 100, at least for the general population of high school seniors. Scores have a maximum score of 800 and a minimum score of 200, and scores have increments of 10. So 640 is a valid score, but 638 is not. And so technically, because it's truncated not truncated, but ends at 800 and lower bound of 200, it's not normal because normal goes to positive infinity and negative infinity. And also the fact that it increments of 10 is also not normal because normal can be, is continuous and can have any decimal values. And also it's not really normal because high school seniors, the people who take the SAT is not the general population of high school seniors. The people who take the SAT are seniors who intend to go to college, and so that's going to be different as well. Okay, but anyway, we won't worry about that. Let's say we're going to take a random sample of 15 students, and we want to know what is the sampling distribution of the sample variance S squared. All right, so do you guys remember from 100B, I think, what is the sampling distribution of the sample variance? What theoretic distribution would you use? Chi-squared, okay, good. How many degrees of freedom? N-1 is, like, if you're not sure, N-1 is a good number for degrees of freedom. But it's actually, but in our case, the standard deviation of the population is 100. So, what do we do? So maybe you remember, maybe not. It doesn't matter. What we're gonna do is we're gonna just simulate our sampling distribution. So here, I'm gonna get a random sample of 15 values drawn from the normal distribution, mean 500, standard deviation 100. I'm going to round this to the nearest 10. So you round to the -1 place, which will do this. And then if any of the values are over 800, we replace it with 800. If any of the values are less than 200, we're going to replace it with 200, just so we don't get any non-existing SAT scores. Okay, and then so here's one random sample, 15 values, 15 potential SAT scores. And what is the variance? The variance of this sample is 10,120.95. Okay. And what kind of variances are possible? If somebody says, hey, this is an unusual variance, do you have anything to dispute or say it's not that unusual? Not right now. Not right now, we don't. Okay? But what we're going to do is we're going to do this a bunch of times. Okay? Whoops. So here, I'm going to do 10,000, 10 to the 4, 10,000 of these times. I'm going to do this 10,000 times. Every single time, I'm taking a random sample of 15 values. Every single time, I'm going to kind of turn them into SAT scores by rounding them to the nearest tenth and making sure the max is 800 and the min is 200. And with each sample of 15, I'm going to calculate the variance and store them in this vector sample variances. Okay, and so after doing this, the largest variance I've observed was 29,838. The smallest variance I observed was 1,540. And the mean or median variance is something around 9,600, 10,000. Okay, and here is the distribution of variances that I get. Okay, so, you know, as expected, we're not going to get any negative variances. Okay, and yeah, we see, okay, values over 25,000 are quite rare. Values of 10,000 is not that unusual as far as sample variances go. If you did want to use the theoretic distribution, this quantity, s squared times n minus 1 over sigma squared, this would follow a chi-square distribution with n minus 1 degrees of freedom. So if I scaled the sample variances by this number n minus 1 over sigma squared, the result would follow a chi-square distribution. So here, if I scale all of these things, the sample variances times n minus 1 over sigma squared, I'm going to get scaled values. And if I plot the scaled values and I plot the theoretic chi-square density against it, we see, yeah, there's quite a close match between the chi-square density and the sampling distribution that I simulated. Okay. All right, but let's see if we can use this for statistical inference, right? So if we didn't remember the sampling distribution follows a chi-square distribution or how to adjust for it and things like that, you know, you don't have to worry about it. You can run parametric bootstrap. And I think once you're comfortable, once you do parametric bootstrap a few times, I think you can become comfortable with it. And the idea of doing something like this doesn't feel all that strange. So let's say, you know, somebody gets 15 SAT scores, randomly selected SAT scores, and the sample variance is 20,000. And the question is it reasonable to believe that this sample was not randomly drawn from a population with mean 500 and standard deviation 100? Maybe this is not randomly selected. This is selected, you know, somebody went out of their way to choose these students. Or maybe they're coming from a different population or something like that, okay? Is it possible to just get a sample variance of 20,000 by random chance, okay? Well, what we do is we go back to our sampling distribution that we simulated and we say, well, how often do we get a value of 20,000 for our variance just by random chance? How often does that happen? And the answer is not very often, okay? We look at all of our sample variances and we say, well, how many of our sample variances are greater than or equal to 20,000? Sample variance is greater than or equal to 20,000. This is going to be a logical vector of a bunch of trues and falses, and we can say what proportion are true. And only 1.2%, 0.012 of these sample variances ended up over 20,000. So yes, it could happen when you draw a random sample from the normal distribution. It could happen, but it doesn't happen very often. It happens with a probability of 1.2%. So if we see a sample variance of 20,000, either we have to assume we were one of those lucky 1.2%, or we have to assume that maybe this wasn't randomly drawn, or there's something else going on to explain why we got a variance of 20,000. And that's how we would do a hypothesis test with Bootstrap. Does that kind of make sense? We feel okay with this? All right. What if we wanted to do a hypothesis test, or not a hypothesis test, but just wanted to get some probabilities for the highest score in a classroom, okay? So this is a bad assumption, but let's pretend we had a classroom of 25 students, and these students, we're going to assume these students are a random sample, okay? Again, that's never the case, right? Maybe, I don't know, did you have a homeroom class or something? maybe, but in general, like probably in high school, like you were in the classes where all of your peers were also expected to go to college, I imagine, and things like that. Whereas, maybe in elementary school, it was just kind of, well, and even then, in elementary school, it's not even random because you're all living in the same neighborhood, and, your neighborhood is generally going to be more similar to each other than different neighborhoods and stuff. So a random sample of students, I don't know how this is going to work, okay? But what is the sampling distribution of the highest score in the class? And what is the probability that in a classroom of 25 students, the highest score is 750 or higher? How do we answer questions like this? Okay, so the theoretic distribution that's used to calculate extreme values like the maximum value is technically the Gumbel distribution. And I don't know if you've heard of the Gumbel distribution or ever used it, but I'm not that familiar with it, and I don't even know if I'd be confident to use it, right? So I might be able to say like, okay, this is the theoretic distribution, but I'm not confident in how we would go about using it. So on the other hand, I'm a lot more comfortable with parametric bootstrap because I can say, well, I know how to randomly draw a sample. I know how to calculate the statistic I'm looking for, and I can do this a bunch of times. So here we're going to draw values, again, from the normal distribution, this time 25 values from the normal distribution. I'm going to convert them all into SAT scores by rounding them and capping the max at 800 and the min at 200. And then for each sample, again, I'm repeating this 10,000 times. For each sample, I'm going to find the maximum value in my sample, the highest score in this classroom of 25. And we're going to store this in highest underscore score. Okay? And so after doing this 10,000 times, no surprise, the maximum value is 800. So that means at least somebody scored 800. Okay? And the median is something like 690. So in a random classroom of 25 students, around half the time, the highest score was, around 690 or higher, 690 or lower. So 690 is the median. Okay, and then this seems kind of low, but I guess when you do it 10,000 times, it could happen. Here was one time we had a classroom of 25 randomly chosen students that were, I guess, particularly kind of low performing, and the highest score in that classroom of 25 was 540 or things like that. Okay, so these are this is the distribution. And if we were to graph this, this is the resulting distribution we get. And we can here see that, actually, the Gumbel distribution would not necessarily be using the theoretic distribution might not be the best idea because the SAT has a max score of 800, we actually don't get kind of the smoothed out tail that we would expect. And so here we see kind of a little, secondary peak here of 800 showing that, there's kind of an artificial cutoff here, okay? And so now we can say, okay, well, what's the probability that the highest score in a classroom of 25 students is 750 or higher? So here I can take that vector of highest scores, say how many of them are over 750, and we get something around 16%. So with a sample of 25 random students, there's around a 16% probability that the highest score is 750 or above. So 750 would be considered, I think, a very good score on the verbal section. Okay, what would happen if we had a random sample of 50 students rather than 25 random students? What do you think would happen to this probability? The probability that your highest score is 750 or higher. Okay, well, with a bigger classroom, now you have you're throwing more darts at the wall, right? So now you have a better chance of kind of hitting this 750 or higher. So with 50 students, that probability goes up to around 29-30%, okay? And it's easy, okay? All we have to do, we just take the exact same code, and I just say, you know what, now I'm drawing random samples of 50 rather than 25. And for each sample, I'm going to calculate the max value. And we're going to see how many times was that highest score over 750. So we're getting sampling distributions for each of these things, and we can use them to calculate these probabilities. Oh, you know what? I've forgotten. View quiz answers today. Let me just go ahead and give you your first two view quiz answers. The first two are A and C. A as in apple, C as in cat. A as in apple, C as in cat. Okay, let's say a high school has 200 students in its senior graduating class. I don't know how big your high schools were. What's that?
Like about 800 to 1,000 in graduating class for public.
800 to 1,000 in graduating class? I think I had maybe like 500 in mine. I don't know. 200 in yours? Okay, so. All right, so let's say your high school, 200 students in senior graduating class. And the school administration this year is very proud of itself because 10 of its students scored 700 or higher on the SAT verbal. So that they go, oh yeah, 10 students over 700. That's great, okay? And they say, we're doing a great job preparing our students for college. Look at these SAT scores. All right, is this something to be proud of? 10 students out of scoring 700 or higher in a class of 200 students? Or is this just kind of like, eh? Okay, so the question will be, does this sample provide evidence that the student body is something other than a random sample drawn from the general population with a mean of 500 and standard deviation of 100? Okay, how would we answer this question? Okay, what I'm going to do is I'm going to calculate the sampling distribution for the 10th highest score. We're going to say, okay, what is the 10th highest score? If I have a random sample of 200 students, let's find the 10th highest score, and let's see how often that 10th highest score is 700 or higher. Okay, so here I'm going to draw 200 values from the normal distribution, and then we're going to sort them and take the 10th highest score. And we're going to store all of those values. We're going to do this 10,000 times, 10,000 samples of 200. And each time we're calculating the 10th highest score. And then we say, how often is that 10th highest score greater than or equal to 700? And we get a value of 3.5%. Okay, we get an empirical value of 3.5%. So this says, according to our simulated sampling distribution, if 200 scores are drawn from a normal population, it's not that likely for the top 10 students to have scores of 700 or higher. And it would be reasonable to say that our sample of students is not randomly drawn from a population with mean 500 and standard deviation 100. It could be, but it's also reasonable. If your significance level is 5%, we're getting a p-value less than 5%. Okay. Now, whether the school administration can claim responsibility for these high scores is debatable. And certainly there could be all kinds of other things going on surrounding the high scores and things like that. But this is, something like this happens. If it were a random sample, it would happen with only a probability of 3.5%. Okay. Does that kind of make sense as far as how we are conducting hypothesis tests using parametric bootstrap here? All right, and so if you're comfortable making assumptions about the population and saying it's going to have these parametric distributions, then you can use parametric bootstrap. Let's talk about non-parametric bootstrap. So non-parametric bootstrap is probably your kind of default bootstrap that somebody might be talking about. Non-parametric bootstrap is not going to make any parametric assumptions on the distribution of the population. Okay, so yeah, section 3, non-parametric bootstrap. So we are not making any kind of parametric assumptions. So we're not going to say the population has a given shape. We're not going to say it has a normal shape. We're not going to say it has this mean. We're not going to say it has the standard deviation. We're not making any kind of parametric assumptions about the population. The one assumption, and it's a big assumption, but the one assumption is that the sample we have, if it's we're going to assume that it's a randomly drawn sample, and the big assumption that goes with it is that if this is a randomly drawn sample, we can expect it to be representative of the larger population. That's the one assumption. It's a kind of a big one, but that's the one assumption. We're going to say the sample I have is randomly drawn, and therefore it is representative of the population. And if it is representative of the population, then I can simulate the population by taking my current sample and just duplicating it infinitely many times, or just a whole bunch of times, and this is now going to create this kind of pseudo population. So it's kind of like in Photoshop, there's like this rubber stamp tool. Like if you have a patch of grass, you can kind of like copy this patch of grass and copy and paste it a whole bunch of times, and you can kind of create like this whole field of grass, right? And the idea being that when you look at this patch of grass, it should be representative of all fields of grass, and therefore I can just kind of copy and paste it, and it's going to just look like a big field of grass. Now, if there is something weird in that patch of grass, like you have this bright yellow blade of grass that's huge or something, and you were to copy and paste that, then the field is going to end up looking funny because you're going to see this repeated weird blade of grass showing up everywhere. And same kind of idea. If you have a random sample and you just happen to get this crazy outlier in your random sample, and we're going to say, let's duplicate this and create a big population based on this, that random outlier is going to get duplicated way too many times, okay? But the hope is the random sample you have, and again, you don't know if it's representative or not, but we're hoping that your random sample is representative of the population, and that therefore it is safe to just kind of duplicate this a whole bunch of times to kind of create like a fake crowd, okay? And so, you can imagine like a computer game where it's like trying to simulate a crowd or something, and it just really has only like, 10 different character models or something, but then it just kind of like copies and pastes them everywhere, and it says, oh, look, here's a big city or crowd or something like that. So that's the big assumption here. Now, we don't actually have to take our sample and duplicate it a whole bunch of times on our computer. What we can do is we can take our sample and we can draw with replacement. Drawing with replacement is mathematically equivalent to taking your sample and duplicating it a whole bunch of times as a stand-in for the population. And so once we do that, so now we have a kind of a stand-in for our population, then we can generate the sampling distribution. So just a quick recap or comparison of these things. If your data was obtained via random sampling, you can use non-parametric Bootstrap. If your data was obtained via random sampling and you're comfortable making parametric assumptions, then you can do parametric Bootstrap. If your data came from an experiment with random assignment, then you can't do Bootstrap, you have to do a randomization test. Okay, so random assignment means exchangeability, and that leads to a randomization test. If you have random sampling, then you can do Bootstrap. Okay, but in all of these cases, we're generating a sampling distribution by using kind of randomness, either random shuffling for random assignment or random resampling for Bootstrap. The example that we're going to take a look at comes from the textbook. This is the textbook, the Ziefler textbook, and they wanted to do this study. And so I'm going to just go ahead and read this. And it says, the Center for Immigration Studies at the U.S. Census Bureau has reported that despite shifts in the ethnic makeup of the immigrant population, Latin America and Mexico specifically remain the country's greatest source of immigrants. Although an average immigrant is approximately 40 years old, large numbers are children who enroll in U.S. schools upon arrival. Their subsequent educational achievement affects not only their own economic prospects, but also those of their families, communities, and the nation as a whole. Stamps and Bowen studied the educational achievement of Latino immigrants by examining a random sample of the 2000 decennial census data, a subset of which is provided in the CSV. One interesting research question that has emerged from the research is whether there is a link between where the immigrants originated and their subsequent educational achievement. Specifically, the question is if there is a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries. So there's this file, latinoeducation.csv, and this is coming from the 2000 census, so it's already 20 plus years old now, but they're curious. These are the different variables, and one of the variables is this educational achievement level. Okay, and this is some number ranging from 1 to 100, in which higher values indicate higher levels of educational achievement. Let me just show you the kind of the head of this table. Now, unfortunately, so they provide this data dictionary, but unfortunately, there were no details about this number or what these numbers mean. So when we see a score of 59.2, I have no idea what that actually means. Like, I don't know if this means the person graduated high school, if they graduated college, if they got a two-year degree, 4-year degree, went on to graduate school, or they dropped out of high school. I have no idea. Okay, so unfortunately, we don't have much context. The only information we have is higher numbers mean more educational achievement. So I don't know what it means to have a 30.6 and what it means to have a 67.6. Okay, so unfortunately, that information is not provided. But these are questions that I think we should be asking and are important. So anytime you encounter a data set and you have some kind of score, you should ask, what does this score even mean? And where did this score come from? Okay. There's other variables: immigration year, immigration age, which is the year in which they arrived, and the immigrant's age at the time of immigration. English is the individual fluent in English, yes or no. And Mexico, or Mex, and did the individual immigrate from Mexico? And that's a binary variable, either yes, this person came from Mexico, or no, they did not. Okay, and so this is what we have. All right, and so what we're going to do is we're going to take our data set and we're going to just calculate some summary statistics. Okay, so we have immigrants from Mexico versus immigrants who came from other Latin American countries. We have 116 who came from Mexico, 34 came from other Latin American countries. And if we look at the achievement score and calculate the mean was 64.5 for people who did not come from Mexico, and the mean was 58.6 for people who came from Mexico. We had these standard deviation numbers. And the question is, is there a difference? Okay, 64.5 versus 58.6. Okay, when you calculate the difference between these two numbers, that difference is something like 5.9. And the question is, could this be a result of just randomness, or is there actually a difference? Okay, and again, even if we find a difference, evidence of a difference, it's hard to draw any kind of conclusions regarding why or what is happening. All we're saying is just, in the year 2000, when this data was gathered, is there a difference here? Okay. So here's just some more exploratory analysis. Here's a box plot. This is for immigrants from Mexico, immigrants from other Latin American countries. There seems to be a bit of a difference for the median, but it's hard. It's hard to really say much. Here's two kind of density plots. Now, unfortunately, this plot gets a tiny bit confusing, just because at this point of intersection between the red and blue curves, like, they have very similar slopes. So it's like you could almost imagine But anyway, you have the red curve and then the blue curve, and they have different things. And is there a difference? Is there a significant difference between these two kind of density curves? And again, hard to say. The traditional analysis would be something like a t-test for two independent samples. That would be kind of our traditional analysis. Our null hypothesis would be that there's no difference between the mean education score or mean education achievement score for Mexican immigrants versus other Latin American, Latino, Latinx immigrants. That difference would be 0, and the alternative is that the difference is not equal to 0. So we would just do a t-test, and we get a p-value of 0.04597. So just under 5%. So depending on what your significance level is, you might say, okay, our p-value is significant, it's under 5%, or if you have a lower significance level like 1% or 2%, we would say your p-value is not significant, and what kind of conclusions you can draw from there would depend on that. So this is where we'd use a t-test. Now a t-test assumes that your sampling distribution of the mean follows a normal distribution, which perhaps is a safe assumption because you have a fairly large sample, 34 in one group and 116 in the other group, so maybe that assumption is okay. That's where we are, okay? When we do non-parametric bootstrap, what we're going to do is we're going to resample the original data with replacement. We're assuming that our sample is representative of the population, and sampling with replacement is again equivalent to taking infinite numbers of copies of our sample and having that stand in for our population. So to do this, we want to create a sampling distribution for the quantity, the mean education score for Mexican immigrants versus the mean education score for immigrants from other Latin American countries. And we want to know, what that sampling distribution looks like. Our null hypothesis says there's no difference, that it's centered at 0. And so if the null hypothesis were true, all of the values for education achievement levels will be coming from the same population. That immigrants who came from Mexico, their education achievement scores are coming from the same population as immigrants from other Latin American countries. So I would just draw the values from the same kind of pool here, and that's what we will do if the null hypothesis were true. So if the null hypothesis were true, the achievement scores for Mexican immigrants come from the same population as the achievement scores for other Latin American immigrants. With parametric bootstrap, we assume our sample of 150 observed achievement scores is representative of the entire population. And what we're going to do is, to kind of see what kind of differences we can get, we're going to draw 2 random samples, one of size 116 and the other with size 34, because that's what we have in our samples. And we're going to calculate the difference between these two means a whole bunch of times. And so this is what our code would look like, okay? I'm sampling that column. So this Latino $achieved, this is a column of 150 values, and I'm going to sample 116 of those values with replacement. Sampling 116 of these values with replacement. I'm going to just throw this into group A. I'm going to take 34 values from this sample 34 values with replacement, throw that into group B, okay? And so who ends up in group A and who ends up in group B is just completely random, and they are both coming from the same population. This is what would happen if the null hypothesis were true. If the null hypothesis were true, everybody's coming from the same population, and whatever differences we get are just a result of random sampling. So I'm going to keep track of all of these differences, and we want to know, how often do we get a difference greater than our observed difference? Our observed difference back here was negative 5.92. And we have a non-directional alternative, so we want to check both tails, so we're going to use an absolute value. Now you have to be careful when you do the absolute value. in my case, my observed difference was negative. And so if I just did absolute value of the differences, how often are they greater than this? 100% of them are going to be greater than negative 5.9. Okay, so that's not the right approach. So what we have to do is we have to take the absolute value of the observed difference, which will now become positive 5.92, and we want to know how often were our observed differences greater than or equal to positive 5.92. And here we get a proportion, again, just under 5%, 0.0465. So, which aligns with our t-test. When we did the t-test, we got a p-value of 0.04597, so around 4.6%. And here we're getting a p-value of, again, right around 4.6%. So depending on your significance level, we would say, yeah, there either appears to be or there doesn't appear to be a difference. Okay, what if we wanted to do parametric bootstrap? I'm going to run out of time. Let me go ahead and give you your last view quiz answer for today, which is the letter E. E as in elephant. E as in elephant. Okay, what if we want to do parametric bootstrap for the same population? Okay, so with parametric bootstrap, what we're going to do is we're going to just simulate values coming from a normal distribution. We're going to assume that the education achievement scores come from a normal distribution, and if the null hypothesis were true, we're going to assume that they're coming from the same population, the same normal distribution. So I need to say, okay, what mean should I use and what standard deviation should I use? So I'm going to use the mean of all 150 values, not separated by whether they came from Mexico or some other country. Okay, we're going to just put all of them together and calculate the mean. And then we're going to take all the values together and calculate the standard deviation. We're going to say under the null hypothesis, both populations, both groups are coming from the same population. So we say I'm going to draw 116 values from a normal distribution with mean M and standard deviation S. I'm going to draw 34 values from the same normal distribution with mean M and standard deviation S. Okay, we're not using different means and different standard deviations. And we have group A and group B. We're going to just calculate what kind of differences can we get just from random sampling. If we just randomly sample values from the same population, can we end up getting different means, and what kind of differences can we get? So we're going to keep track of all of these differences. And what do we get? We get a p-value very comparable to all of the other p-values we've observed of, basically 4.6%, 4.65, something right around there, which kind of makes sense. Here it just says, all of these, when you get a bunch of things that are in agreement, that's a good sign. So we're all getting p-values right around 4.6%, which, again, depending on your significance level, is going to determine what kind of conclusion you're comfortable making. And again, we have to be careful whether let's say you're using a 5% significance level and you decide to reject the null hypothesis. What is the conclusion you're going to make? You're going to just say, well, at least in the data that we've observed, I don't think this is the result of random chance, and therefore we're going to assume that, or we're going to come to the conclusion that there is some kind of difference between the education achievement score of immigrants who come from Mexico and education achievement score of immigrants who came from other countries. But as far as why that's the case or what's going on, we're not able to answer that at all. Okay, that requires more research and a deeper understanding of kind of immigration and things like that. When you do parametric bootstrap, we're basically assuming that the values come from a normal distribution, and we want to probably check, is that a reasonable assumption? So this is the scores, distribution of achievement scores, and I don't know if this looks normal, so maybe this isn't a good thing. This is kind of the QQ plot, again, not quite a straight line, so maybe assuming that it's normally distributed is not the best idea. But then again, a t-distribution we can probably work with, because the t-test assumes the central limit theorem, and kind of the requirements for the central limit theorem is that your data is randomly sampled and it's large enough. And I think our samples are large enough, at least, to apply the central limit theorem. Whether or not we are comfortable with our p-value and our conclusions, that's a different question. Okay, we will end here for today. Friday's lecture will be, I'm going to teach online on Friday, so I won't be on campus on Friday, so I just sent out a link for that. But other than that, we'll see you later. Have a good rest of your day.